Good morning. Let's see. Yes, thank you. So one of the key things that we want to modulate, both in health and disease, has to do with cognitive functions. And we've been looking at how different methods of brain stimulation can be used to do that. So we know that cognitive processes, they are emergent properties of rich network interactions. So there must be a way for regions that are far remote apart in the brain to communicate with each other in an efficient manner. And oscillations have been proposed to be one of such processes. And indeed, it seems to be that, or has been proposed that brain networks emerge from cortical dynamics and cortical-cortical interactions that generate frequency-specific neural oscillations. Indeed, brain oscillations at different frequencies have been associated with specific behaviors, with specific cognitive processes. And not only the frequency or the amplitude of those oscillations, but also phase synchronization seems to play a role and seems to have to do with how information passes in different regions of the brain, how remote regions communicate. So I've been listening today, both from Teal and from Caroline, that you can use brain stimulation methods to look at this network dynamics, and you could use things like methods like transcranial alternating current stimulation to investigate how, if you selectively modulate a particular oscillation, what is the impact on behavior. So the idea here, what these techniques can give you, is going beyond correlations, as Teal was saying. So instead of the typical approach has been for many years that you get participants to the lab and they perform a particular task while you measure their brain activity. What we want to do here, what we want to do now, is to go beyond this and be able to directly manipulate particular oscillations, particular brain activity, and see how this impacts on behavior. And again, with techniques like TACS or TMS, for many years we had this sort of black box, using the same analogy that Teal used, very in sync. And then we measure behavioral changes, right? But what we want to do is to go beyond this. So we kind of need to open this box and see what's going on when we perform stimulation. And so we're talking about how important it is to using imaging modalities, and you heard about electrophysiology modalities, EEG and MEG, to give you an idea of what's going on during simulation. And I'm going to talk about combining TACS with fMRI. Why would you want to do this? Why would we want to use fMRI? So I think the most obvious reason has to do with spatial resolution. So when we use fMRI, we're talking about spatial resolution of the order of millimeters, and this allows you to look at these large-scale networks that I talked in the beginning that support cognitive processes. And you can go not only look at cortical regions, but also subcortical regions. The second reason has to do with still the difficulty that we have in cleaning artifacts imposed by the stimulation, cleaning artifacts in EEG and MEG. And although when you do fMRI, you indeed lose that frequency range that you can get from EEG and MEG, so you can't anymore make, it's not that easy to make a claim that they're actually manipulating alpha or beta. However, there seems to be a relationship between EEG signals and Bolt signals. So I think, more than 10 years ago, Mantini and colleagues have shown a relationship between the envelope of EEG rhythms and the frequency and fluctuations in Bolt signal at very low frequencies. So in this figure here, they correlate different frequencies with resting state networks. So they saw how different EEG rhythms correlate with resting state networks. Still here we're talking about correlational evidence, and Bechinger and colleagues perform a very interesting study trying to establish a causal link between the power fluctuations they observe in EEG signals and resting state fMRI. So what they did is that they have resting state fMRI, and simultaneously they apply transcranial alternating current stimulation in this sort of amplitude modulation way. So they measure individual alpha frequency in the subjects, and they modulated the envelope of those individual alpha frequencies. So their modulator was a slow frequency, a 1 Hertz, and in one condition they modulated the envelope of the current they were imposing in 2 electrodes, the electrodes in red, so roughly above the motor cortex. And in another condition, what they did was that this power modulations are out of phase, but the individual alpha frequency was in phase. And they observed that they can modulate the functional connectivity within the sensory motor network, so they increase the connectivity strength within the sensory motor network. And this only happened when they have the power synchronized condition. So this kind of shows causal evidence for what Mantini showed more than 10 years ago. And another interesting finding from that study is that this power synchronized TACS was more effective in modulating resting state connectivity in individuals that had a low connectivity between the 2 hemispheres, the left and right hemispheres. And one of the possible applications of the studies has to do with modulation of this connectivity strength in resting state networks. So you probably heard throughout this conference that many diseases are associated with changes in functional connectivity, and this has correlates in behavior. So this perhaps is a way of modulating that. Another interesting study looking at how you can manipulate resting state networks comes from Reinrich and colleagues. And in this case, they use 3 different stimulation conditions. So they use a beta stimulation condition, 20 Hertz, theta, 5 Hertz, and sham. And in this case, they don't see a change in connectivity between M1, so they stimulated M1 and supraorbital contralateral, more traditional sort of montage. They don't modulate M1 connectivity, but interestingly, and here in red, so the plot in red shows the 20 Hertz, so the beta frequency. They show that the correlation that you typically see between the 2 M1s and the motor network disappears during this 20 Hertz stimulation. And they use a phase precession model, the Kuromoto model that's very widely used when you want to look at oscillatory behavior. So they show that the model indeed explains this absence of correlation during the 20 Hertz condition. And this can start providing us also additional information on how local oscillatory activity might underpin network connectivity. So how by changing local entrainment in M1, you have an effect that modifies networks that are related to M1. Okay. I've been, so moving on from resting state network activity, I've been quite interested in manipulating frontoparietal function. And the reason for this is that the frontoparietal network has been involved in many processes, one of them being working memory, which we know there is impaired in many diseases. So I performed this study where we had participants doing different tasks that load differently on the frontoparietal network. So the first task that you see on the left is the choice reaction task. It's a very simple task where participants just have to report the direction of an arrow. And you can increase the difficulty, also the load in the frontoparietal network, by increasing memory load. So what we did was to do a 1 back and a 2 back task. And we did this at the same time as participants received transcranial alternating current stimulation. And in this case, we impose an external oscillation that was either in phase, so we had 2 electrodes, one frontal, one parietal, and the imposed current could be either in phase between the frontal and the parietal or out of phase. And what we observe is that when we have the most challenging condition, so the 2 back condition, during this in-phase stimulation between the electrodes in frontal and parietal, participants got better, meaning that they were faster than in the sham condition or in this desynchronized condition. And indeed, they were as fast as they were for the 1 back condition. So, but as I told you, we want to go beyond just looking at behavior. We want to understand what's going on in the brain when we do this sort of manipulations. So we performed simultaneous TACS fMRI study, and our hypothesis was that TACS will be able to modulate activity and connectivity across large-scale networks, and also this will be dependent on the type of simulation, on the different condition of simulation that we applied. So first of all, we'll look at what's going on underneath the electrodes, and during the 2 back condition, when we imposed this synchronous simulation, we saw a correlation between the activity in the parietal region and reaction times, such that the participants that had a high increase in bold activity were also faster in this task. And I think very interesting what we observe is that it's not only is not very such a local modulation per se, but actually is a whole frontoparietal network. So when we impose this condition, the synchronous condition, the whole frontoparietal network increases its activity. And in the desynchronized condition, we observe a very different pattern. So it's the pattern just below, where we see that the default mode network is more active. And this wasn't the case, so this difference in the profile of activity wasn't observed if we use a different task, so the choice reaction task, which is quite a simple task. Just try to be quick now. So we also saw modulations in functional connectivity. Interestingly, during the synchronous condition, there was an increase in connectivity between parietal region and frontal region, and we didn't observe this in the synchronized condition. Okay, so we wanted to take these results and apply it to patients with traumatic brain injury. So when you have a traumatic brain injury, typically what happens is that you have something called diffusional axonal injury. So because due to movements during the brain injury, what happens is that you have axonal injuries. And this will impact, of course, how communication passes between different regions of the brain. So we've done the same, we applied the same protocol to patients with traumatic brain injury, and in this case, both stimulation conditions led to an increase in the frontoparietal network for the 2 back task, which is a profile slightly different, very different from what we've seen in healthy controls. The next step was to look whether, okay, so we see this increase in frontoparietal activity in patients with TBI. What happens compared to controls? And what we see is that during the sham condition, so when stimulation is off, as we expected, patients have a decrease in activity in the frontoparietal network. And this has been reported before. So is the areas, the blobs in orange, are regions where controls are activating more than patients with TBI. And another typical pattern for patients with TBI is that they have also a change in activity, in this case, the activation of the default mode network during this cognitively demanding tasks. And what we see with when we apply brain stimulation is that this pattern is restored, so we don't see anymore a difference between controls and patients with TBI. Something very similar happens when we impose this desynchronized condition. However, we don't restore completely the pattern in the default mode network. Interestingly, in the patients, there's no modulations in functional connectivity. So it might be that due to this diffusional axonal injury, we actually not passing that information, this phase information, as effectively as it happens in healthy controls. And we also don't see any behavioral changes in the patients. So what we're going to look next is looking at whether FA, so the functional connectivity between different tracks in the brain, can explain this, because we saw that this is the case when you do a nodal stimulation. Okay, so to very rapidly conclude, so I hope they're convinced that simultaneous TACS and fMRI is a powerful tool to study this causal relationship between oscillations, brain networks, and behavior. One of the things that to keep in mind, and why it's also important to do these techniques together, to apply stimulation while you record brain activity, is just only based on current density models. You're not able to predict what is the impact that you have in the function of brain. And the results that I show you today and others have shown is that TACS is not constrained to the local region where you apply the electrodes, but it's a more complex picture. So it's dependent on brain state, independent on the parameters they use for the simulation. So it's definitely very important to combine this with an imaging modality. And yeah, so some like interesting stuff that we've learned that I want to try is to constrain the face using this ring electrode montages. We talk a little bit about amplitude modulation, and next Nir is going to talk about temporal interference. Will be really interesting techniques to combine with fMRI. And just to acknowledge, oops, not this. Can you go before? Yes, just to acknowledge loads of people that contributed to all this work. Thank you very much.
Thanks a lot, Ines. Thanks.